Welcome back to Metaphor Math, and we're on to 5a in the set theory chapter of Intro to Analysis by Rosenlicht. And in this problem, we're dealing with a slightly different notation here, but it's the same. We're doing the same kind of set equality, or the way we show set equality, where we're going to show that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. We just have to deal with a new notation here. Let me just outline this notation. What they mean by this index set I. So I is an indexing set, So let me explain what that means. I could mean I'll just say suppose I is equal to the set of natural numbers, so 1, 2, 3, and so on. So I could be equal to the natural numbers. It could be equal to any set that we wanted. But in this case, let's suppose I is equal to the natural numbers. Then that means that the union of all I and I of the sets xi can be rewritten as x1 union, x2 union, and so on. It's very similar to summation notation, where let's say I was an I. Usually, you see set notation from I is equal to 0 to, or in this case it would be 1 to infinity, and you have AI, and that's equal to A1 plus A2 plus and so on. But in this case, we're just instead of this infinity here, we're rewriting that from 1 to infinity in a different way, where we're just saying that I is in the set of natural numbers I, or where I is equal to, little I is in the big set, the uppercase I, where uppercase I is this set of natural numbers here. So it's just another way of writing set notation, summation notation, but with unions. So hopefully that gives you a better sense of what this notation means and can help us solve the problem a little bit better. So 5a, we're showing another set equality here. So we're going to do it in the same way that we've done before. So just take a general element. Let's show that the left-hand side set, let me just write this real small here. Left-hand side set is a subset of right-hand side set. So this is part 1 here, because we obviously have to show that the right-hand side set is a subset of the left-hand side set. So let x, b, and b intersect the union of for all I and I of xi, the sets xi. And remember, since every element in this left-hand side set here has the property of being in B intersect union xi for all I and I, then if we can show that this x must also be in the right-hand side set, then we've shown that all x that have this property of being in this left-hand side set, and therefore all x in the left-hand side set, must be in the right-hand side set. Okay, so let's go on and see what this means. So if x is in B intersect the union of I and I of all x and I, then like usual, by definition of the set intersection, x is in B and x is in the union of I and I for all x and I. So first I want to go over what this means. What does it mean to be in the union of really what we don't know how many elements are in I. It could be infinity, it could be an uncountable infinity, it could be a finite number. I could be 1, 2, 3, and 4. Big I, that is. So we don't know what this indexing set I is. But what we do know, and let me just illustrate this. Let's first think about what does it mean for an element x to be in x union y. Well, we know that x is in x or x is in y or both, but another way of saying this is x is in at least one of x or y. And if there was a set z here, then we could know x could be in x or y, x could be in x or z, x could be in x, y, and z, or x could be in y and z, or y and z. So, but what we do know for sure is x is in at least one of x or y or z. So we can do the same thing here for kind of an indeterminate number of sets. We know that x is in at least one of these xi's. So we'll say that here. So let me switch back to this purple color. X is in B, and x is in xj for at least, let me just give myself mark off some room here, for at least one j and I. And j is just any number. If suppose that I were the natural numbers, then j could be 3, j could be a trillion, j could be 7. It doesn't matter. But for at least one j and I, if I was a natural numbers, for at least one natural number, x is in x sub j. So if x is in B and x is in x sub j for at least one j and I, then by definition of set intersection, x is in B intersect x sub j for at least one j and I. And remember, since it means, since this, if x is in the union of, for all I and I, of xi, then that means that x is in at least one I, xi, x sub I, rather. X is in at least one xi for some I and I. Then if x is in B intersect x sub j for at least one j and I, then that means that since B has no indice associated with it, we can just say that we can just substitute this B intersect xj into here for this definition of an x being in at least one xi for some I and I. So this set could be this set over here. We could just substitute this to be some x or some, let's call it y. Then that means x is in y sub I, the union of all y sub I for I and I, and replacing what this B intersect x sub j is for y, that's the same as saying that x is in the union of I and I for B intersect x sub I. And we've done it. We've shown the left-hand side set as a subset of the right-hand side set because we've just shown that this x must also be in here, in this right-hand side set, the union of all I and I for B intersect x sub I. So let's go the other way. Where we're going to show that the right-hand side set, and let me actually just write it here, that the union for all x, or not for all x and I, for all I and I of B intersect x sub I is a subset of B intersect the union of I and I of all xi. So we're going to do the same thing. So let x be in the union of I sub I of all B intersect x sub I. Then that means that x, by definition of what it means to be, or not really by definition, but what it means to be, what we just talked about up here, what it means to be in the union of any number of sets, that means that x is in at least one of B intersect xi, or rather xj for some, or actually I won't say this at least one B intersect xi, And that implies that x is in, for some j, we don't know which j it is, but we know that for some j in I, x is in B intersect x sub j for some j in I. And that means, or if x is in B intersect x sub j, then by the definition of set intersection, x is in B and x is in x sub j for some j in our indices set j and our indices set I. And if x is in B and x is in j, well, let's first think about what this statement means. What does this statement mean? Well, if x is in x sub j for some j in I, then that implies that x is in at least one xi for I in I, which is the same as saying, but by what we talked about up here, that x is in the union of all I in I for x sub I. And since x is also in B, then we can say that x is in B, intersect by the definition of set intersection, and by what we just derived right here, that x is in B intersect the union of I, and I of all xi. So pretty much this problem is really hinging on, or heavily hinging on, this definition of what it means to be in multiple, to be in the union of multiple sets. It means that you must be in at least one of those sets in that union. So if x is in at least one of the xi for I and I, then x must be in the union of all of these xi for I and I. So that means that x is, and since x is also in B, then B must also be in B and the union of xi for all I and I. And we've done it. We've shown that the right-hand side set is a subset of the left-hand side set. And we're done with this problem.